minutes. We will have your introduction for the participants just within a couple of minutes for this fourth session of online faculty development program on photonics, which is sponsored by Atal Academy, New Delhi, and organized by Department of Physics, Electronics, and Photonics, Rajarshi Shahu Mahavidyalaya, Latur, Maharashtra. We have with us Honorable, renowned scientist, author of many books, many physics books, Honorable Dr. Ajoy Ghatak, sir. I request Vrunda Raute madam to introduce today's guest. Vrunda Raute madam, please. Raute madam, your voice is not audible. Please.
Yes.
Is it audible?
Yes,
Audible now?
Yes.
Yes, ma'am. Please start, ma'am.
With great pleasure, I'm here to introduce Professor Dr. Ajoy Ghatak, sir. Actually, there will not be single person in physics community who do not know about sir. Sir has completed Master of Science from Delhi University in 1959 and he received degree of Doctor of Philosophy from Cornell University in 1963. After a short stint as a research associate at Brookhaven National Laboratory, Professor Ghatak sir joined the Indian Institute of Technology in Delhi in 1966 and retired as an emeritus professor of physics in 2007. Sir is currently Professor Meghnad Fellow of NASI, the National Academy of Sciences, India. Sir has research interest in fiber optics and quantum mechanics. He has about 170 research publications. He is recipient of the S.S. Bhatnagar Award of CSIR for outstanding contributions in physical sciences in 1979 and Galileo Galilei Award by International Commission for Optics in 1998. In 2003, Sir was awarded by Esther Hoffman Baylor Award by the Optical Society of America in recognition of his outstanding contributions to optics education. In 2008, Sir received Spy Educator Award in recognition of his unparalleled global contributions to the field of fiber optics research and his tireless dedication to the optics education worldwide. Sir has been listed as noteworthy physics educator researcher by Marquis Who's Who. Sir is fellow of Optical Society of America, Optical Society of India, Institution of Electronics and Telecommunication Engineers. In 1995, he was elected fellow of the Optical Society of America for his distinguished service to optics education and for his contribution to the understanding of propagation characteristics of gradient index media, fibers, and integrated optical devices. Sir has authored around 20 books, including his undergraduate textbook on optics, which has been translated to Chinese and Persian. His other books include Quantum Mechanics, Theory and Applications, Fiber Optics, Experiments with Light, Lasers, Optical Electronics, and a popular book on Albert Einstein. The Story of a Genius. Presently, Sir is writing book on optics 7th edition in multicolor. Sir, we as a physics teachers very eager to see theory of colors in multicolor. We always read you, but today we have rare opportunity to listen you. So I will request you to start today's session on fiber optics revolution. Please,
Thank
sir.
you, Vrinda. Can you hear me?
Yes, sir. Yes, sir. It is audible.
Please put your presentation slideshow.
It is already there on the slideshow.
Sir, then you do one thing. Please unshare and then share with the desktop because the slideshow is not visible.
Okay. Now, where do I?
Share and you share entire desktop and then open PPT, sir. Left side, there will be text.
Can you now see?
Yes, yes, sir. Yes, sir.
Can you see now?
Yes, sir. Full slideshow.
sir.
It is.
All right.
Okay. Thank you, sir. Please continue.
Can I start?
Yes, sir.
Thank you very much. Thank you, Dr. Yadav, for inviting me to this photonics workshop that you have organized for college teachers and research students. I'm going to spend I've been given about 90 minutes. So let me know 5 minutes before when I have to stop. I'm going to speak on fiber optics revolution. And before I start, I thought I will tell you all that this COVID crisis is, of course, has done tremendous amount of damage to the country. But you know, this evolution of these webinars is a remarkable thing that has happened. Education is now free, almost free. And sitting in Delhi, I can teach in remote villages, not only in India, but also abroad. So it's a technological revolution that has taken place. And I'm very happy to be participating in it. Maybe I'll talk about it a little more if there is time. Why life has I wanted to tell you about this because these days many institutes have stopped teaching engineering to optics to engineering students. But suddenly the study of photonics, what is photonics? Photonics in which electronics electronics works on the movement of electrons, and photonics does the same thing as electronics but uses photons. So there's a study of light has suddenly become very important, and I will try to answer in the first few slides why that is so. In fact, in the year 2015, UNESCO declared it as the International Year of Light. 2015 was declared as the International Year of Light. Why? Because 1000 years back, 1000 in 1015, Alhazen wrote the first book on optics, Kitab al-Manazir. He was in Mesopotamia, which is now in Iraq. So this is the cover page of a translated edition of Alhazen's book on optics, and using which people in Europe studied optics. So it all started with this book. So in proclaiming 2015 as the International Year of Light, the United Nations recognized, and read this, applications of light science and technology are vital for existing and future advances in medicine, energy, information and communication, fiber optics, agriculture, mining, astronomy, architecture, archaeology, etc., etc., etc. Today, phone calls have become free. Video conferencing like this has become almost free, and that is because of fiber optics and lasers. So it is all optics. Then, few years later, UNESCO declared May 16th as the International Day of Light. All colleges, including your college, should celebrate every year May 16th as the International Day of Light. Why May 16th? Because the first successful operation of the laser was done by Theodore Neumann on 16th May 1960. Here is a photograph of Theodore Neumann, who should have got the Nobel Prize. But he did not. He was nominated, but he did not get the Nobel Prize, which is sad, because he fabricated the first laser that created a revolution. The discovery of lasers has led to tremendous benefits to society in communications, healthcare, and many other fields. One of the main, as you all know, one of the main advantages of the laser beam is its directionality. The light coming out from an ordinary bulb spreads in all directions. But the light from the laser is highly directional. And because of that, it can be focused to a narrow spot. So if you look at a 2 milliwatt laser beam, 2 milliwatt, and your eye lens has a focal length of 2.5 centimeters, then the area of the focused spot is about so much, and the intensity will be 3 megawatt per square meter. So such high intensities will damage your retina. So never look into a seemingly innocent low power laser beam. So whereas it is safe to look at a 1000-watt bulb, but it is very unsafe to look at a 2 milliwatt laser beam. And because it can be extremely high intensities can be generated, we can make very important devices which have been created for the industry and also defense. This is a photograph, and I'm sure all of you are familiar with this institute, Radha Ramanna Center for Advanced Technology, RRCAT, in Indore. Dr. Brahmanand Upadhyay is one of our former students. Here is a laser that is fabricated there, focused by a lens and drilling through concrete. Here is a 2 kilowatt fiber laser cutting through steel. I'm sure all of you are aware of this, all this. And the laser beam is used for eye surgery extensively. Cataract surgery, eye retinal detachment and everything. And then laser beams, there are 8 arms, 10 arms. 10 laser beams are being focused, and they can create temperatures of millions of degrees Kelvin, which will result in generation of fusion power. The above photograph shows the setup at the Lawrence Livermore Laboratory in the United States. It can deliver more than 500 trillion watts of peak power to the target. Right now, the amount of fusion power that comes out is slightly less than the amount of power that is pumped in. But very soon, I hope, in a few years probably, we will have a situation where the power energy that is liberated from the fusion process will be greater than the energy that is supplied. And then we will have a fusion reactor. When that happens, there will be no problem of power. So laser-induced fusion is an extremely important area on which is going on. I thought I should mention that the 2018 Nobel Prize in Physics, how important light is, was awarded for groundbreaking inventions in the field of laser physics. Half of the prize money went to Arthur Ashkin. He was at that time 92 years old. Unfortunately, he passed away only a few weeks back. For optical tweezers and their application to biological systems. What is a tweezer? You see, this is a tweezer, and you are holding a small diamond here, small diamond. So this is, as you all know, is a tweezer. So Arthur Ashkin developed the first tweezer. And I will tell you the basic principle. As you all know, Einstein in 1905 said that light consists of discrete quanta of energies known as photons, which later came to be known as photons, whose energy is h nu and whose momentum is h nu by c. So So each photon carries a momentum, which is h nu by c, where h is the Planck's constant, nu is the frequency, c is the speed of light in free space. This was a revolutionary concept and eventually led to the development of quantum theory. Someday I will tell you, hopefully, the development of quantum theory. So let us suppose I have a tennis ball or a cricket ball hitting a stationary train on a frictionless track. So when it rebounds, it transfers a small amount of momentum to the train, very small, but it does transfer because the momentum of the tennis ball or the cricket ball changes direction. And so therefore, a small amount of momentum is imparted to the train. And if it is really on a frictionless track, it will start moving. Similarly, if a light beam strikes a mirror, then since each photon carries a momentum, the direction of the momentum changes, and so therefore a small momentum is imparted to the mirror. And so therefore, if you have a laser like this, the photons change direction. So initially they were coming in this direction, and now they are going in this direction. So a small momentum is imparted to the lens in this direction. This is just from the conservation of momentum. If you have two beams like this, then this beam will make it move upwards. This beam will make it move downwards, and it will be almost stationary. The amount of momentum that is transferred is very small, but finite, not zero. So when a light beam falls uniformly, no momentum will be transferred to the lens. Now here is a very beautiful photograph. You see, this is a laser beam. The maximum intensity is here. And as you go off axis, the intensity becomes smaller and smaller. So this ray, so this is about, say, few millimeters in diameter, And this ray, and this may be a bead or a biological substance about a 1 micron in diameter, 1/1,000,000th of a meter in diameter. So this ray comes in, changes direction. So it imparts a force to the bead in this direction. This ray comes in, changes direction. It imparts a force in this direction. The net force is very small in the forward direction. On the other hand, if the bead is moved away from the axis, then this ray is more intense than this ray. I have shown this by a thicker line here. Ray number 2 is thicker than ray number 1. So this momentum is larger, transfer of momentum is larger. So this force is larger, and this force by this ray is smaller. Simple momentum consideration. And the bead will tend to move towards the center. So when the bead is displaced from the beam center, the larger momentum change of the more intense rays cause a net force to be applied back towards the center of the laser. Thus, the bead is held near the center of the laser beam. It tends to move slightly in the forward direction. So these photographs are by Ronald Quibbler in Germany. So to avoid that, you use a focused laser beam. Then what happens is that there is no electronics, there is nothing there, just light. So a focused laser beam is made to fall on the sphere, which in addition to keeping the bead in the center of the laser, also keeps the bead in the fixed axial position. It's a beautiful application. So this is, if you go to YouTube and write optical tweezers, and I hope I can show you, let me see if I can show you the video. This is the actual, can you see the video, Dr. Yadav?
Video is not visible, sir.
Okay, so
Picture, it's still picture.
Video is not visible.
Not visible.
Oh, doesn't matter then. So you go to YouTube and write optical experiments on optical tweezer, and these are micron size and which can be manipulated to move around. It's a beautiful experiment. It's a beautiful device, all optics. So look at that video. This is the, so then the other, so these optical tweezers have been a revolution. And it's not a very complicated device, but as with all devices, most of these things are imported from outside. There are companies which are now trying to make optical tweezers in India. Let us hope it comes through. Then the remaining half of the Nobel Prize, of the 2018 Nobel Prize, went to Gerard Murrow and Donna Strickland for CPA. CPA stands for chirped pulse amplification. And what one does is, you take a short pulse, you pass through a device in which the group velocity increases with wavelength. I have explained this very carefully in my latest edition of optics book, which has come out. So this, because of dispersion, the pulse broadens in time. The peak power comes down. And it gets chirped. As you can see, the horizontal axis is the axis. Here the frequency is larger. The front end has a higher frequency, and the trailing edge has a lower frequency. If you take the Fourier transform of this pulse, then the bandwidth, the frequency width will be the same as this. There are no new frequencies that are getting generated. But since the peak power comes down, it can be amplified by a conventional amplifier. And if you use this pulse, then the amplifier may have been damaged or burnt out. But since the peak power has come down, I amplify it and then pass through group. This is also a chirped pulse. Everything is linear. Group velocity increasing with wavelength, the pulse then compresses and produces an intense increase in peak power. Of course, okay, I will send Dr. Yadav a small paper that I have written and which can be circulated to all.
Yes, sir. Yes, sir.
So such ultra-short, high-intensity laser pulses produced by CPA find extremely important applications in industry. For example, in cancer treatment, in many commercial products, in eye surgery, etc. Indeed, since 2011, CPA certification has been used in 24 million eye operations. And because of that, Donna Strickland and Gerard Murrow received the half of the Nobel Prize. Then the 1997 Nobel Prize in Physics was awarded to Stephen Chu, Cohen Tannoudji, and William Phillips for development of methods to cool and trap atoms with laser light. In fact, they used the tweezer to cool and trap atoms. So when this Nobel Prize was announced in 1997, Arthur Ashkin was very unhappy, but we are very glad that eventually he was recognized. In 2018, it took them 21 years to recognize that work, the greatness of that work. So, there is, even in Nobel Prize, there is a lot of golmaal. No, not golmaal. Things are not fair. And one of the greatest mistakes of the Nobel Committee is, can you all guess? Not awarding the Peace Prize to Mahatma Gandhi. That is one of the greatest mistakes of Nobel Committee. There are many mistakes. You see, one person gets the Nobel Prize, there are 10 others who deserve it. So that is the disadvantage of the Nobel Prize. And then we had Denis Gabor receiving the Nobel Prize for holography, and then for quantum optics, Glauber and Hall and Panish. And then we had the 2014 Nobel. I am just trying to tell you, convince you, the importance of optics. And 2014 Nobel Prize in Physics was awarded to Akasaki, Amano and Nakamura for the invention of blue LEDs. And then the 2017 Nobel Prize was given to these three gentlemen for contributions to the LIGO detector and observation of gravitational waves, confirming general theory of relativity. But what is LIGO? For laser interferometer gravitational wave observatory. So it is all optics. It's a gigantic Michelson interferometer. So here you have a laser beam, and then it is a beam splitter here, just like in a Michelson interferometer. It's a 4-kilometer long beam, and there is a reflector, and coming back, and then part beam gets reflected here. The two beams interfere to produce a fringe pattern. So it's just optics. 1.3 billion light years back, there is 1.3 billion light years away, there was a violent collision between two black holes, and gravitational waves are created which were detected by the LIGO. If you go to YouTube, you will find very nice experiments. Professor Brian Greene explaining the LIGO experiment. Go there and see. So it's all optics. There are 4 laboratories right now, 3 I think, and one is under construction in Japan, and one is planned in India. So I hope that will be also in Maharashtra, Pune, and I would like to see the LIGO working in India. So at that point of time, there will be a large number of people who will be required who have a knowledge of laser physics and interferometer optics. So I hope I have been able to tell you that why study of light or of photonics has become extremely important, not only for students of physics, but more so in engineering. And as I told you earlier, that even in IITs, they now some of the IITs do not teach optics anymore. This is a step in backward direction. Optics, quantum theory, electricity and magnetism must be part of all syllabi. It has become very, very important. What I am going to tell you in the remaining part of the lecture is a bit on fiber optics, a technology that has created a revolution and has made phone calls or video conferencing like this free. It's a revolution that has happened. 25 years back, I would make a call to Bombay and it will cost me 100 rupees for 3 minutes. And my salary would be also much less than what I get right now. Today, it is free. You must ask yourself how that has happened. The price of anything only goes up. How come the phone calls have become free? It is the development of the optical fiber, development of lasers which can be modulated with extreme rapidity and detected. So that is all optics and optical engineering that has revolutionized communications. So as you know, Maxwell said that light is an electromagnetic wave, gamma rays, X-rays, ultraviolet, visible, infrared, they are all electromagnetic waves. They have different frequencies. All wavelengths travel in free space, that is vacuum, with an identical velocity of 299,792,458 meters per second. That is now an universal constant. This is the visible region of the spectrum. The blue end of the spectrum has a wavelength of 0.4 micron. The red end has a wavelength of about 0.7 micron. And the corresponding frequency for the 0.5 micron is 600 terahertz. For 0.6 micron, the corresponding frequency is 500 terahertz, where 500 terahertz is 500 into 10 to the power of 12 hertz. That is 5 into 10 to the power of 14 hertz. 1 terahertz is 10 to the power of 12 hertz. For example, you see here radio broadcast at 98.3 megahertz. So that is 98.3 into 10 to the power of 6 hertz. I'm sure all of you are familiar with that. So refractive index of a medium, as you all know, is given by C by V, where C is the speed of light in free space and V is the velocity of light in vacuum. And you all know Snell's law, when a ray hits a denser medium, it bends towards the normal. This is an actual experiment. So when a ray hits a rarer medium, denser to rarer medium, it bends away from the normal. So you can have an angle where the angle of refraction is 90, and all angles, that is the critical angle, and all angles greater than that, total internal reflection takes place. And this is a actual experiment of total internal reflection of light at the interface of water and air. This is water and this is air, and the beam is undergoing 100% reflection. 100% energy is reflected. So the first experiment on light guidance took place by Daniel Culloden, professor of physics at University of Geneva. He took a bottle, and you can take something like a Pepsi bottle, 2 liter. You make a hole in it, let the water come out, and you use a laser pointer. And as the water comes out, you can trap the light beam. Trap the light beam. So the light gets trapped. So although the phenomenon of total internal reflection has been known for 300 to 400 years, guidance of the light beam because of total internal reflection, the first experiment was done in 1841. So this is basically the structure of an optical fiber. I'm sure most of you know this. This is the core and this is the cladding. Cladding is usually pure silica, ultra pure silica, silicon dioxide, and its refractive index is 1.46. And the core is also silica, but doped with a slight amount of germanium, so that the refractive index becomes slightly larger. So this medium is denser than this. So for all angles of incidence greater than the critical angle, total internal reflection takes place. That is how light gets guided through the fiber. If you have a bare rod, then also total internal reflection will take place. But if it comes in contact with any material, then light will quickly leak out. So therefore, the necessity of a cladding. Since light can quickly leak away from unclad fibers, necessity of a cladding. And so therefore, even if it comes in contact with other materials, light will not leak out. The credit for the concept of a cladded fiber using cladding is given to Van Heel in Holland and to Hopkins and Narendra Kapani in the United Kingdom. Kapani was born in India, Punjab, and he went to UK, did his PhD with Harold Hopkins. Unfortunately, I could not find a photograph of Van Heel and Hopkins, but Narendra Kapani had coined the term fiber optics, written a book on fiber optics actually. So this is the transverse dimension of the transverse cross-section of the fiber, and the core diameter multimode fiber is about 100 microns or 50 to 100 microns. And this is the cladding, which has a 1% less refractive index than the core. And the core cladding diameter is about 125 micrometer every time, always. And then there is a jacket to shield the cladding. So 125 micron, you know that the thickness of the human hair is about 80 micron. So it is that dimension that I am talking about. And for a single mode fiber, I don't think I will have the time to tell you what is a single mode fiber, where it supports only one mode, maybe some other day. The diameter is about 10 microns. So this is how a fiber, the structure looks like. So even if you bend it, light gets trapped in. So these are hair thin. This is the thickness of the fiber. This is the fiber, a single strand of a fiber, and light gets guided through it. How do you see that? That is because of the phenomenon of Rayleigh scattering. Why do you see a fiber glow when you bend it? So this is my single mode fiber. The inner core is about 10 microns in diameter, and N2 is about very slightly different from this, 0.3%, about 1%, not more than that. And this diameter is always 125 micrometers. Here is about 80 microns. So I will tell you a little bit about scattering. What is scattering? As you all know, that if you have a positively charged alpha particle, it sees a positively charged nucleus, so coming from a long distance, it gets repelled and changes direction. So this is known as, this phenomenon is known as scattering, and it gets scattered by an angle theta. So you see, here is a light. You can do this experiment at home and show to your students to explain what is scattering. Here is a simple laser pointer, and you have a water, distilled water. And in this glass, you have distilled water, put a few drops of milk. Now the milk particles, colloids, scatter light. And you can see this scattered light. You cannot see this scattered light here. You can see, this is the fact that you see a red line here is because of scattering. So in fact, this is the trajectory of a comet. Comet comes in, this is the movement of the Earth, and this is the comet comes in from one direction and goes in another direction. This is scattering in the field of the gravitational field of the sun. So the Rayleigh scattering, which is due to atoms and molecules, is proportional to, inverse proportional to the fourth power of the wavelength. That is, higher the wavelength, smaller will be the Rayleigh scattering. So therefore, the red light will undergo more scattering than the blue light. Sorry. Smaller the wavelength, greater will be the scattering. So blue light will undergo more scattering, more Rayleigh scattering than the red light. And that is why the sky is blue. Because sun has we have an atmosphere. Let us suppose it consists of nitrogen and oxygen molecules, and the sunlight gets predominantly scattered in the blue color. Small wavelengths undergo more scattering, and so therefore the sky is blue. And therefore the setting sun is red, because the blue component gets scattered out. And we see the red component, predominantly the red component in the light that comes out of the sun. The red color of the setting sun is due to Rayleigh scattering. The phenomenon that the scattering dependent on the wavelength was first discovered by Tyndall, but an explanation was given by Rayleigh. So many people call it scattering. But since Lord Rayleigh gave the theory and he was more famous, so it is now known as Rayleigh scattering. You know, Raman effect was discovered by his student K.S. Krishnan. So I always say that Krishnan discovered the Raman effect, the Raman shift on 28th February 1928. But Raman got the Nobel Prize and he became famous, and he will be appearing in textbooks for centuries to come. And Krishnan, many of you may not know the name also. So getting a Nobel Prize, getting credit is always not very fair, in my opinion. So here is a photograph of the man on the moon. And see the beauty of the photograph. It's the daytime and the sky is completely dark because there is no atmosphere on the moon. So the sky is not blue. And the shadows are completely dark because there is no scattering. So there are three areas in which optical fiber plays an important role. Fiber optics in image transfer, fiber optics in optical communications, and devices like fiber amplifiers, fiber lasers, fiber Bragg gratings, etc. See, in 1930, much before the discovery of laser, Heinrich Lamm, a medical student in Munich, Germany, first assembled a bundle of transparent fibers to transmit an image. If you take a large number of fibers and align them properly, so that this is the front end, this is the back end, this is the front end. So if they are aligned properly, we say it is a coherent bundle. It is difficult to make a coherent bundle. So here there are dark spots here, there are dark spots here. So I have shown the transfer of the image T through the bundle of optical fibers. So a bundle of optical fibers can have 10,000 or even more optical fibers, hair thin optical fibers, very carefully stacked in. So this is an experiment, say 1 centimeter or so, and this is a small portion of that, and you can see the individual ends of the fibers, very nicely put. And this is again an amplified version. So here is a human hand holding a fiber optic bundle and light coming out from there. And you can insert in the human body down the throat or through the anus and see the inside of the human body. Here is a stomach ulcer being seen. And if you put a laser beam there and a lens at the tip of that bundle, then you can carry out surgery. So it's a remarkable discovery that has made. Remarkable device. Medical endoscopy, fiber optic endoscopy. It's all light. And without opening up the stomach, you can do operations. So you can do many, you can kill cancer cells, and things like that. Another application of fiber optics has been in solar fiber optic lighting. Now, this is not a glass fiber. This is a plastic fiber, one fiber whose diameter is about 1 centimeter, 11 millimeters. Cladding diameter is 11 millimeters, and the core diameter is 8 millimeters. These are plastic fibers. And you see, here is an experiment. Plastic fibers transport light. This is not solar energy of the type that we talk about. This is transporting light from the roof to the inside of the room. And here is a thick optical fiber. And this is a gentleman in Oak Ridge National Laboratory in the United States. And you can bring in light. Very simple technology. And I have been trying to myself advocate this as much as possible, because in a country like India, it can be a great contribution. So you receive the sunlight and there is no electric wire, nothing. And you just carry through the optical fibers and illuminate rooms. Of course, you can illuminate rooms only when there is sunlight. On a very cloudy day, it will not work. So these are the solar collectors, not solar cells, not solar cells. And here is an actual photograph. And this is now being used extensively in Western Europe, Netherlands. There is a company which is making this. And there is no reason why we should not have this technology in a country like India, where there is so much of sunlight in states like Maharashtra, Gujarat, Rajasthan, Uttar Pradesh, Delhi, Punjab, Bihar. And for example, in schools and colleges, in villages, if there is lack of electricity, you can use solar light, but you require plastic fibers. The unfortunate part is that the plastic fibers are very lossy. They have a large attenuation. And also they are expensive. They are made in China. We should make them. I have told the polymer people to make them. But we are still not making good quality plastic optical fibers. So now I will go over to optical fibers in communications. Higher the frequency of the carrier waves, higher would be the information carrying capacity. You see, in the good old days, when you receive a radio signal on your radio, it is much smaller than you use in transmitting images and which you see through your television, because you require a higher carrier frequency to transmit images. So this is the electromagnetic spectrum that I had shown. And the radio waves are here. Your cell phones operate in the megahertz. So it has been always the engineer's dream to use optical frequencies, because then we can carry a large amount of information. So light frequencies, as I told you earlier, are 100 terahertz, which are much larger than the radio wave frequencies and the microwave frequencies. Microwave frequencies are gigahertz. So light frequencies are about 1,000,000 times more. So light waves are capable of carrying much larger amount of information. And typical bit rate required for a voice communication is about 64,000 bits. For a telephone, standard television is about 100 megabits per second, 100 pulses per second, and high density television about 1.2 gigabits per second. So let us suppose I have an analog signal and voice frequencies go from 0 to about 4,000 hertz, 4,000 hertz. So in order to transmit all frequencies from 0 to 4,000, it should be sampled at least twice the frequency, that is 8,000 times per second. This is a theorem in electrical engineering. And then I sample each sample represented by 8 bits. So for a single voice channel, 8 into 8000 becomes 64 kilobits per second. So this is a typical fiber optic communication system. I have a signal, analog signal, like I'm speaking on the telephone, and I digitize it and then pass through the optical fiber. And then as it passes through the optical fiber, it broadens in time, which is known as dispersion. I don't have the time to go through dispersion. And it also attenuates. There is a loss, a small loss in the fiber. But if I'm able to detect each pulse, I can retrieve the original signal. The first experiment on optical communication was done by Graham Bell, Alexander Graham Bell, in 1880. He called it the photophone. In this system, sunlight was modulated by a diaphragm and transmitted through a distance of about 200 meters in air to a receiver containing a selenium cell connected to the earphone. So this is the first experiment in which light beam was used to communicate the voice. And Graham Bell called it the photophone. And he said that the photophone was the greatest invention I have ever made, greater than the telephone. Between 1880, not 1980, 1880 and 1960, there was not much work in communication using light beams. Then a revolution occurred. And as I told you, what was that revolution? The first laser was fabricated in 1960, and immediately scientists and engineers started talking about optical communication system. Initially, there were this open air communication systems, but because of the presence of cloud, dust, etc., the beam will undergo attenuation. And so therefore the necessity of a guiding medium, the necessity of a fiber. And then came a revolutionary paper. In 1966, a very profound prediction was made by Charles Cow and George Hockham of Standard Telecom Laboratory in UK, who said that glass fibers represent a possible practical optical waveguide with important potential as a new form of communication medium, provided the tiny impurities in glass are removed, attenuation, that is the loss, is brought below 20 dB per kilometer. What is a dB? Most of you will know that input power divided by output power. If I take the logarithm to the base 10 and then multiply by 10, then this is the loss of power in decibels. So if P1 is equal to P2, then log 1 is 0. So 0 dB power loss means P1 is equal to P2. On the other hand, if P2 is equal to half P1, half of the power is lost, then that is a 3 dB. 10 log 2 is 0.3, log to the base 10, 0.3, so 0.3 into 10 is 3 dB. So 3 dB loss corresponds to 50, I'm sure most of you will know this. And then power loss by a factor of 10, so log 10 is 1, so that is a 10 dB loss. Power loss by a factor of 100, that is 2, log of 100 is 2, so 20 dB power. Power loss by a factor of 1000, that is a 30 dB power loss. So if you have an amplifier and you say that this is a 30 dB gain, that means there is a power amplification of 1000. Power amplification of 1000. So what happened was, initially the losses in the glass that you use in your window panes have a huge loss because of the presence of tiny metals, water inside the glass. So these three, so after the prediction of Cow and Hockham in 1966, globally, people started purifying glass. And eventually, these three gentlemen in Corning Glass Works produced fibers, silica fibers, whose loss was about 17 dB per kilometer. You see, they said that the loss, Charles Cow said that loss should be below 20 dB. So they produced loss at 17 dB per kilometer. And today, by 1980, fibers were produced with a loss of about 0.2 dB per kilometer. It's a tremendous technological achievement. Now, understand this curve carefully. The vertical axis is the loss in pure silica in decibels per kilometer, and the horizontal axis is the wavelength. So as the wavelength increases, the loss becomes smaller and smaller. That is due to Rayleigh scattering that I had mentioned. And these small peaks that occur are due to impurities, water, iron, and so on. And they are difficult to remove. But by 1980, purification was so high. So the lowest loss in ultra pure silica occurs at 1.55 micron, and that is 0.2 dB per kilometer. And remember, Cow had said that the loss should be below 20 dB per kilometer. So it's a factor of 100 below that. So this should be 1.55 micron. So most optical communication systems now work at 1.55 micron. We have now lasers available at this wavelength, and amplifiers also available in this wavelength. There is another window here at 1.3 micron. In fact, the first and the second generation optical communication systems operated at 1.3 microns. But you can have sophisticated technologies to remove these water peaks. And this is a curve that I have obtained from Sterlite Technologies. Sterlite Technologies in Aurangabad make such fibers. And I wanted to tell you that they make communication grade optical fibers, and they export the optical fibers to different countries. So Charles Cow received half of the 2009 Nobel Prize in Physics. Once again, George Hockham was neglected. The paper was Cow and Hockham. Charles Cow received the 2009 Nobel Prize in Physics for groundbreaking achievements concerning the transmission of light in fibers for optical communications. This is when he received the Nobel Prize in 2009, and this is in 1966. I think he has recently passed away. So the chair of the Nobel Committee said Charles Cow's discovery made in 1966 led to a breakthrough in fiber optics and revolutionized the way in which information can be transmitted globally. So why glass fibers? Glass is a remarkable material which has been used for thousands of years. And the beauty of glass is that it does not solidify at a discrete freezing temperature, but gradually becomes stiffer and stiffer and eventually becomes hard. In the transition region, it does not have a fixed melting point. It can be drawn into a fiber. So this is a glass rod, and which is, when you heat it, it becomes soft. And then you can draw it into the fiber. So this is a preform. I hope you can see this. This is how a preform looks like. And then you can, when you heat it, it becomes soft. And it can be drawn into the form of a fiber. This is actually a glass rod, the core of which is doped with erbium. It looks like the same. So when you draw this, you have an erbium doped fiber. So this I got from Kamal Bhadra at Central Glass Ceramic Research Institute. And this This fiber drawing machine is there also. So there was another breakthrough in 1970. Alpha Rao in Leningrad, the room temperature operation of semiconductor lasers, for which the 2000 Nobel Prize in Physics was awarded to Alpha Rao. So let me consider one aspect, how to manage the attenuation. So you have a 1 milliwatt pulse. It passes through 80 kilometers of fiber. So the lowest loss is quarter of a dB. Quarter of a dB multiplied by 80 is 20 dB. So power loss is by a factor of 100. So 1 milliwatt becomes 10 microwatts. There should be enough optical power for error-free detection. So to travel long distances, we need to amplify optical amplifiers. So this is a conventional repeater electronic. I will not go into that. But can fiber losses be compensated optically? I thought I will tell you a little bit about it. We can have direct amplification of optical pulses by using EDFAs, erbium growth fiber amplifiers. So as you all know, if there is an atom sitting in the excited state, it can emit radiation of the frequency nu, which is E2 minus E1 by H. This is known as spontaneous emission. Einstein predicted stimulated emission, this is stimulated absorption. That is a radiation of a particular frequency of this frequency. H nu is approximately equal to E2 minus E1. We'll pump the atom from the ground state to the upper excited state. So the light will be absorbed. So this is known as stimulated absorption. The light beam stimulates the absorption. Then Einstein, as you all know, predicted stimulated emission. So here is a light beam of this frequency, which is in an excited state, and the radiation stimulates the emission, resulting in an amplification of the beam. One photon does not become two photons, as many books write. I have tried to carefully explain that in my book on lasers. One photon does not become two photons. It is the light beam inside a cavity which gets amplified. So this is the basic principle of laser, light amplification through stimulated emission of radiation. Light amplification, that is the acronym of laser. Now, what Einstein had predicted was just stimulated emission. But light amplification was predicted by Richard Tolman in 1922. And Einstein also predicted that the probability of stimulated emission is the same as probability of stimulated emission. And so therefore, if you have a radiation, you see normally most of the atoms are in the ground state. So there will be more stimulated absorption and lesser number of atoms in the excited state, less stimulated emission. So because there will be more stimulated absorption, it will result in an attenuation of the beam. On the other hand, if I am able to achieve population inversion, that is more atoms in the excited state than in the lower state, then there will be more stimulated emission, less stimulated absorption, resulting in the amplification of the beam. No one thought that you can achieve a state of population inversion because it violated thermodynamic equilibrium. In fact, it was 1951 that Charles Townes realized that one could have optical amplification by using population inversion and invented the ammonia beam. So I consider a fiber the core of which is doped with erbium atoms. The concentration is about 440 to 400 pieces parts per million. So these are the energy levels of the erbium atoms, ions. This E3 minus E1 is about 1.3 electron volt. This corresponds to a wavelength of about 980 nanometer. So if you calculate the frequency and multiply by h nu will be about 1.3 electron volt. So you see the erbium doped fiber, you pump it, you shine 980 nanometer light, and atoms will go from E1 to E3. This E3 level, which is a broad band, not a sharp level, and so therefore it is not just 980, it may be 970, 990 nanometers. It will immediately de-excite. It is a non-radiative transition. There is no light is emitted, no photon is emitted. And this is a metastable state. It has a very long lifetime. 10 millisecond is a small time, but this is 10,000 times more than this. This is 1 microsecond. This is 10 milliseconds. So 10,000. So if you have a strong pump, then it will excite the levels from E1 to E3. That will immediately come down to E2. And the atom will just sit there. And if the pump power is large, you will have a state of population inversion. And E2 to E1 is about 0.81 electron volt, which corresponds to 1.55 microns or 1550 nanometer, approximately. So light from the pump supplies energy to elevate the erbium ions to the excited state. And then propagating optical signals sees an inverted medium and through the process of stimulated emission gets amplified. So this is what an EDFA looks like. You have about 20 meters or 10 meters of erbium doped fiber. So this, for example, when you draw it, you become an erbium doped fiber. It looks like an ordinary fiber. So you have a pump laser at 980 nanometer. You couple that to the erbium doped fiber. And if this pump power is large, it will excite the erbium atoms from E1 to E3, and then it will quickly come to E2. And if the pump power is large enough, then there will be larger number of erbium ions in the level E2 than in the level E1. So an incoming signal will see a state of population inversion and will get amplified. So this is the basic acronym of laser. Light amplification through stimulated emission of radiation. So I have told you the basic physics of, what time it is? Basic physics of optical amplification. And now you put this fiber between two mirrors which will act as a resonator, and you will have a laser. So these are the erbium doped fiber developed at CGCRI in Kolkata. I thought I will tell you. They commercialized and sold it with Nest Cochin. This is a company, high-tech company in Cochin, which manufactures and sells erbium doped fiber amplifier. And one of our former students, Dr. Ramdas Pillai, is president of New Photon Technologies based in USA. They also have a company in Trivandrum. They make this compact EDFA. This is a 25-cent coin, which is of the same size as a 2 rupee coin. And this is how the amplifier looks like. And he's making a lot of money. It provides up to 40 milliwatts of output power. The unit works at 3.3 volts with a power consumption of less than 1.5 watts. That is to drive the laser, pump laser. So you can have an EDFA because of the broad bands of erbium of 30 dB gain. The vertical axis is gain and the horizontal axis is wavelength. So gain is about 30 dB. That is power amplification of 1000. And so therefore you can simultaneously amplify all wavelengths between 1530 nanometer to 15. This is in the infrared region. And so therefore, in a WDM system, wavelength division multiplexed systems, you have a large number of wavelengths, something like 200 or 500 wavelengths. I've shown them by different colors, but they are all in the infrared region. They are multiplexed into a thin fiber and periodically amplified at far. And as I told you earlier, it also broadens it. So there is also a dispersion compensator. I don't have the time to do that, but in my book it is given there. So this is how the two repeaters can be spaced about 80 kilometers, and then there is a dispersion compensator. This is how the layout of a typical fiber optic system looks like. So the EDFA was discovered in 1990, around that, and before that only one wavelength could be propagated through the optical communication system. Suddenly, when the EDFA got started manufacturing, by 2001, 200 wavelengths were simultaneously propagating through one hair-thin optical fiber. This is 2001. Now things are much better now. And the total capacity is 100 terabits per second through one hair-thin optical fiber. And because of the EDFA, and because of the availability of low-loss optical fibers, the costs have come down. So in 2001, Alcatel propagated simultaneously 256 wavelength channels through one optical fiber, sending 10.2 terabits per second of information. That implies 150 million telephone channels through one hair-thin optical fiber. So now these fiber optic systems are crisscrossing the entire world. They are being laid every day under the ocean, under the ground, beside the railway tracks, and so on. This is a typical cable, which may consist of 12 fibers or bunch of fibers. And you will have every 80 kilometers repeaters. And this repeater is nothing but an erbium doped fiber amplifier. And it's probably a dispersion compensator. And under the ground, under the sea, it's a remarkable technological achievement that has happened. Even inside India, all major cities are connected through optical fiber. No, thank you. So the capacity distance is the bandwidth, the amount of information that is increasing exponentially. So your erbium doped fiber amplifier, which are extensively used in fiber-based devices, was invented in 1987 by David Payne and his collaborators at the University of Southampton and Emmanuel Deservier and collaborators at AT&T Bell Labs. The ETFA brought about a revolution in fiber optic communication system. And fiber optics and development of ETFAs have made phone calls and video conferencing almost free. So the basic components of the laser as you all know, are the active medium. So the erbium doped fiber is an active medium. Then you must have an optical resonator, which provides frequency selection and optical feedback. So what is an optical resonator? You have a light beam, certain frequencies will get amplified by periodic reflection. Okay. So, Dr. Yadav, you have to, the tea has to be supplied by you.
Yes, yes, sir. Yes, sir. Yes.
So 1
Yes.
watt, 20 watts and 1 watt. So you see,
Yes.
you take a erbium doped fiber and slowly increase the pump power. And this is an experiment done in our laboratory. Initially, the horizontal axis is the wavelength. You get what is known as the power as a function of wavelength, which is known as the fluorescence spectrum. And when you increase the power beyond a certain level, all of a sudden, the ends of the fiber act as reflectors, and you will get sharp peaks, and it starts lasing at different wavelengths. A beautiful experiment. So you see, since you are all teachers, this is what a fiber laser consists of. You have a pump, you have a mirror at the end, and this is a erbium doped fiber or a doped fiber. This is usually neodymium doped fiber. So let me tell you what I used to do when I used to teach at IIT Delhi. I will take a fiber out of my pocket and I will show the students the fiber. Then I will take out another fiber, which would look just the same, and I will tell them this is an erbium doped fiber. So this is an active medium. Now in this active medium, if I put the pump, 980 nanometer pump, it will create a state of population inversion between two levels which have a wavelength difference of 1.55 micron. So an incoming signal will get amplified. So first I will tell them the concept of optical amplification. And that is what the acronym stands for, light amplification through the stimulated emission of radiation. Once they understand that, so first I will tell them what is an ETFA. Then I say that you put between two mirrors and you have a pump laser and you will have a laser. So that is how I would explain them the laser, and they will, and show them the experiment, and show them the experiment. In 1961, sorry, कितना time और है?
Sir, you can conclude, and we will have some questions from participants.
Okay.
Yes, please.
It is 11:20. So let
Yes,
me do for 5 more minutes. Alice Snitzer
Yes,
took a glass
yes.
fiber
Please.
whose core contained uranium ions, wrapped the fiber around a flash lamp, and when suitable optical feedback was applied, a laser was produced. Thus, only 1 year after the demonstration of the first ever laser by Theodore Myman, the first fiber laser was, and it is a great technological device. So even in RRCAT in Indore, there is a 40-watt continuous wave fiber laser. This is a dated thing. Maybe they have done better. But in my opinion, there should be many such laboratories in India which are manufacturing lasers. So you can use laser welding, hole drilling. So I will just spend 5 minutes on another device, fiber gratings, in which in the core of the fiber, you have a periodic refractive index variation. So for example, you have a non-reflecting film, you have a lambda by 4 N0 thick film. This beam will be out of phase of this beam. You read this in your BSc class, and you have, these will destructively interfere and will produce darkness. So this is known as a non-reflecting film. And based on that, we did the Newton's rings experiment. The interference between the light reflected from the lower part of the plano-convex lens and the upper part of this glass plate produced these beautiful Newton's rings. This glass has is an ordinary glass, and there is a non-reflecting film. Here you can see the image of the person who is taking the photograph. So non-reflecting film makes it non-reflecting. So if you have a large number of layers, then there will be a wavelength which will all add up in phase. Each reflection will be in phase for a wavelength which is 2 N0 lambda. Lambda is the periodicity of the grating. This is a grating. This is N0 plus delta N, this is N0 minus delta N, N0 plus delta N, N0 minus delta N. So this is known as the Bragg wavelength. And if you have a white light source incident on a fiber Bragg grating, in which there is a periodic variation of refractive index, then there is a certain wavelength which will undergo intense reflection. And the bandwidth is extremely small. It is about 0.5 to 0.2 nanometers. So you see, you have white light and the reflected light is of one color. So the reflected light from a Bragg grating is more. How do you make such a grating? So when a germanium doped silica fiber is ultraviolet radiation, the refractive index of the germanium doped region increases. This is known as photosensitivity, which was discovered by Kenneth Hill in 1978. So what you do is, as you learn from your BSc, you make two beams interfere to form an interference fringe pattern on the inner surface of this core cladding interface. So wherever there is a maximum intensity, the refractive index increases. Wherever there is a zero intensity, There is no change in refractive index. So if the fiber is exposed to a pair of interfering ultraviolet beams at 240 nanometer, then in regions of constructive interference, the refractive index increases. And you can change the period of the grating by angle, by changing the angle. So you can make a fiber Bragg grating of any periodicity that you want. So this is the fiber. There are now many fiber FBG writing facility in India. So see the beauty of this experiment. I have one single fiber in which I write a grating which reflects lambda 1. This grating reflects lambda 2. This grating, this is known as a distributed sensor. On one optical fiber, I have written all the gratings. Now, I observe this in my laboratory and I see a shift. Whenever there is a shift, I know if the blue line shifts, actually all the waves are different and they are all in the infrared region. This is a slide by Professor Tyagarajan and he has shown by red, blue and green so that to tell you that their wavelengths are different. If the blue has shifted, that means this has undergone some strain or stress or something like that. The periodicity has changed. And so therefore, all bridges have now fiber Bragg gratings inside them. And wherever at the fiber Bragg gratings, the reflected spectrum is recorded 100 miles away. That is the beauty of optical experiments. They say that there was a major tragedy which happened in US. A bridge collapsed. This is an actual collapse of a bridge. And if they had the fiber Bragg grating based sensors, could have avoided this mission. So today, all construction, all railway bridges, transport bridges, buildings have embedded in it fiber-based sensors. Even the fiber grating, they used it in high supply lines near Kolkata to measure temperature. Because if the temperature increases, the length will increase, the periodicity will increase, and so on. So this is the measurement of temperature by the calculator. So one last slide. And so this is one fiber, erbium doped fiber, which is 0.3 nanometer. You do not put mirrors now. You write gratings on them, on a small portion of that. So the grating acts as a reflector. And you get one narrow wavelength which oscillates back and forth. It's a beautiful device. So you don't require mirrors. So you write grating here and at two ends and you pump it, and then the spontaneous emission will generate a series of stimulated emissions which will go back and forth and will produce the laser. And then this, sorry, we can get amplified, and then there is an isolator and so on. So I can go on, and these are the concepts of modes that are. So I finish here, and just 1 second. Wanted to show Faraday rotation also. So these are the references. Professor Tyagarajan and I have written a book which is slightly advanced, which gives the detailed theory of fiber optics. This is the 7th edition that was mentioned by Dr. Vrinda, which has just come out. And many of you usually ask for the slides and things like that. They are all there. So they are all there. I will send Dr. Yadav the link. So whatever I have discussed today is given in the 7th edition of my book on optics. Then Dr. Shamal Bhadra at CGCRI edited a book on guided wave optics, and Dr. Pral edited a very beautiful book on guided wave component. These are advanced books for those who are interested knowing more about fiber lasers, fiber Bragg rating, supercontinuum generation, and all these things. And then there is another book edited by Professor Anurag Sharma. They are all from our group at IIT Delhi. Then we had a software that Professor Anurag Sharma and Professor Ramanand Tiwari had made. We published it in the form of a book. It is a very nice software, but a more sophisticated software the LightSim, Professor Varshney and Professor Vipul Rastogi at IIT itself, we have developed this, which is made available through Fiber Optica Technologies Private Limited. And then there is a book on beautiful experiments that you can do with fiber optics. And then we wrote a book for school students, but it didn't become too popular. Thank you for your attention. Thank you, Dr. Yadav. What time it is now? Oh my God, time is over.
Thank you, sir. Thank you for very informative and very nice lecture. Dear participants, if you have any questions, queries, then you can raise your hands.
Let me see if there are any questions on the chat box. Where is the chat box?
Chat box is open, but participants have not posted anything, sir. Because that is not accessible to participants.
That is not accessible to the participants?
Yes, yes. Because it is not accessible on mobile phone.
Oh. So how many participants are there right now? Can you?
Right now there are around 100, sir.
100.
Yes.
Okay. Okay. Yes. So I have given you my phone number. My time is up. Sorry. So, but all details are given in the book. If there are any short questions relevant to what I have discussed, please ask me.
Yes, sir. Dear participants, if you have questions, you raise your hands and unmute yourself and ask the question to sir.
No question. So everything is clear.
Yeah.
Thank you.
My throat has also become very dry. Bolo.
Yes. Mohit sir.
Sir, I want to
Kaur madam, please ask.
Sir, there is no question about. I want to just thanks for such a beautiful, so much beautiful lecture. Very nice lecture. I understand, sir, very much clear about everything.
Oh, I'm so glad.
Thank you so much.
Who is
because
speaking?
I belong to electronics and communication engineering, but I don't know about so much about lasers. So today I clear so much concept about lasers. Thank you so much, sir, for such a beautiful and simplify your lecture.
Chalo, I'm so glad. I had worked hard for preparing those slides. I'm so glad, Dr. Yadav, that things have worked out well.
Thank you, sir. Thank you, sir.
Chalo, what I will do is I will send you the paper that I had mentioned. And,
yes, sir. Yes, I will circulate among participants.
And please circulate, and I will also send you the link to this thing, and so I will attach that, and then you can circulate, and the rest are given in the book. So there are about 100 teachers who are participating in this seminar, right?
Yes, yes.
Sure.
1 minute.
Yes.
Now I request Professor Trembak Kendre sir to propose vote of thanks.
Thank you, sir. I'm audible, sir. I'm audible.
Yes, sir. Yes.
Thank you, sir. Thank you, sir. Thank you. Very good morning to one and all. I am Kendre Trembak Uttam Rao. I am here to express vote of thanks for this session. We, on behalf of Department of Physics, Electronics and Photonics, Rajashri Sahu Mahavidyalaya, Latur, pays my sincere gratitude towards the President of Sri Chhatrapati Shikshan Samstha Latur, respected Goparao Patil sir, for moral support for this FDP. I pay my sincere gratitude towards Dr. Madhavrao Ghavane sir, Principal and Director FDP Rajashri Sahu Mahavidyalaya Latur, for granting the permission for the conducting of this FDP. I pay my sincere gratitude towards today's speaker, Dr. Ajoy Ghatak sir, spiritual personality, for elaborating all the aspects about fiber optics revolution, including a deep history of discovery. I am very sure that the session was very informative, storming, as well as eye-opening about the fiber optic communication. All the concept about fiber optic communication are definitely cleared after completion of this session. So thank you very much, sir. Thank you. Again, I pay my heartfelt gratitude towards the coordinator, Dr. Abhijit Yadav sir, for organizing such a grand FDP for us. Last but not the least, our all the participants from different states as well as from different universities for their active participation in this session. Without their active participation, the session is nothing. So once again, I am very thankful towards all the participants. Lastly, I pay my sincere gratitude towards all the technical staff for their technical assistant. Again, I am very thankful to Dr. Abhijit Yadav sir for giving me such a opportunity for expressing my sincere gratitude, and I feel very proud that I am the member of this